Okay, of course in the last little bit, those little r's were just the 2x2 rotation matrices. That's what that was, obviously. Anyway, moving on here. G is, one of these guys, special orthogonal, unitary, special unitary, or symplectic. And if G is the Lie algebra of G, and if T is the standard maximal torus, we can define tau, or equal to tau of frac G, which is a subalgebra of G, is the Lie algebra of the torus, the maximal torus. And so here's what those look like. The Lie algebra of the, the algebra of the Lie algebra of the standard torus of SO even dimensional, special orthogonal even dimensional looks like this. You got these kinds of generators. When it's odd, it's almost the same, and there is a 0 thrown in here. Notice that this is the diagonal matrix, so this is actually a block decomposition. These are these 2x2 blocks on the diagonal, and here you have 2x2 blocks until like the last diagonal entry, which is just 0. Which it's an odd it's a matrix of odd dimension, odd size square matrix. So the Lie algebra of the unitary group, the torus of the unitary group, is just the diagonal matrices with I on the diagonal like that. That's pretty simple. And likewise for the torus of the symplectic, it's not that complicated. As usual, the special unitary, it's got to drag something about that traceless condition, somehow makes this get more complicated. So there's a connection between the first n-1 angles and that last component here like that. So there you have it. Those are the Lie algebras of the maximal tori. And so the image under the exponential of a vector in the Lie algebra of the torus of G, it will be an element of the maximal torus, given by some angles. In other words, you exponentiate something in the Lie algebra of the torus, and you get something in the torus, and that the elements in the tori are, well, what are they? Here they are. So the exponential, for example, of the diagonal of this is the diagonal of the exponentials, because, well, that's very nice. I mean, I have to prove this when I'm working out the generalized eigenvector problem in differential equations. I need this for my so-called magical formula. There it is. So that's a typical thing in the maximal torus of UN. We've exponentiated the algebra to get the group, and the group can be seen to be a rotation. The algebra contains in it the angles by which we rotate, right? So if the torus is, well, I mean, not if, the torus is abelian, that implies that the bracket of the Lie algebra of the torus is 0. So for each x in G, there exists a G in the Lie group such that the adjoint with respect to G of acting on X is an element of the Lie algebra of the torus. Let's think about this for a second here. So this is saying, pick anything you want in the Lie algebra. You can find something in the group such that the adjoint moves it into the Lie algebra of the torus. Curious. Wonder what the significance of that is. I mean, there's deep significance into everything we're saying here. Okay. There's nothing I have said in these which is not worthy of probably a lot more thought. So here's the sketch of the proof of that proposition. Choose r greater than 0 such that the exponential from the Lie algebra to the Lie group is a diffeomorphism on a ball of radius r centered at the origin. By theorem 9.13, there exists a G such that A is equal to G e to the x G inverse in the torus. So the exponential of the adjoint acting G and X is equal to E G x G inverse, which is G e to the x G inverse, which again is A, and that's in T. Interesting. All right, so a skew-symmetric or skew-Hermitian or skew-symplectic matrix B can be conjugated to be equal to A, where A is in the maximal torus. The Lie algebra, I should say, of the maximal torus, as presented in equation 9.7, which was the purple stuff I said earlier in this bit, this bit of the talk. The exponential map from Lie algebra to G is surjective. Well, that assumes that G is either SON, UN, SUN, or SPN. That's nice to know. So again, the exponential map, proposition 9.21, shows that the exponential map is a surjection, in fact, from the Lie algebra to the Lie group in the case of the special orthogonal, the unitary, the special unitary, and SPN. Noticeably missing from this list, of course, is, well, what, GLN and SON, right? Okay. So, definition 9.25 on page 156, the rank of G is the dimension of a maximal torus for G. So the rank of the SO2n and the rank of SO2n plus 1 is equal to the rank of UN, is equal to the rank of special unitary matrices of n plus 1 rank, n plus 1 size. All of these is equal to n, and that follows from just counting the number of parameters in the Lie algebra to the torus, all right? Because the Lie algebra to the torus reveals the dimension of the torus as a submanifold in the matrix group. Now, an element of the torus is called regular if its angles are distinct, and for the SON case, they can't be 0 or pi, because that gives you back like the identity matrix or minus the identity matrix, which is, you know, and there's also a criteria for the sum of these guys. All right, but proposition, if x is regular, x in the torus is regular, then x only commutes with other elements of T. So T is the only maximal torus which contains x. Cool. So those irregular elements, like, you know, I guess they could be more in more than one. I mean, well, yeah, shut up. So an element y in G, all right, now I defined regular in the, we defined regular in the torus just a second ago. Now I'm defining regular in the group. Element y in G is regular if y is equal to the conjugation of x for some regular x in the torus, right? So regular elements in the group are reached by conjugation from regular elements in the torus. And what do we have coming up here? A regular element is contained in only one maximal torus in G. Ooh, cool. So that means that these maximal tori give us some sort of dividing, parsing of the space into these, at least it separates the regular points at least, right, from another. And finally, the punchline here to the whole shebang, the classification of compact matrix groups. And of course this is beyond Tapp's book, but you know, I think after you study his book carefully, you can at least appreciate this result. And these things come to you from how to derive these sorts of things is you have to study the representation of, Lie algebras, semi-simple Lie algebras in particular. And, you know, there's a very well-developed, beautiful theory there that derives these things from looking at a particular construction. And, well, anyway, that's another course in and of itself, but we can appreciate the results at least. The Lie algebra of every compact matrix group is isomorphic to the Lie algebra of a product, G1 to GK, where each GI is one of the SON, SUN, and SPN, right? So in other words, the basic building blocks for compact matrix groups are products of the special orthogonal, the special unitary, and the symplectic groups of order n, All right, he's direct product of these guys and these 5 exceptional matrix groups. Now these are not families of things. These are just there's these 5 specific oddball groups that also appear in the classification. G2, F4, E6, E7, and E8. All of these exceptional groups and their corresponding Lie algebras, they have played a significant story in recent mathematical physics. And I think we're still coming to grips with what exactly they mean. If you are interested in this sort of thing, you absolutely must read the paper by Baez on octonions. Anyway, I think that's all I have. Sorry I didn't prove anything, and I probably didn't make much sense, but anyway, I hope we got something out of it. If nothing else, I've convinced you that you should go read the book so you can actually understand it. Thanks.